Welcome to another podcast. This episode we're going to be taking a look at what the phrase flowing down the gradient means. This is a video which sort of spawned out of our discussion in class today, where we were having a little bit of trouble understanding how heat flows in the heat equation. And I wanted to talk about that by starting off with the law that sort of generates this idea and talk about the difference between the mathematical way to write it versus maybe the physical interpretation of what's going on. So the law which governs this is a law called Fourier's law. And if you've done the reading, you'll note that Fourier's law is sort of an important component of actually deriving the heat equation. And Fourier's law says that the outward flux of heat across a boundary is proportional to the outward normal derivative across the boundary. So there are a couple of things I need to mention in regard to this particular law. First thing is the word normal. So if I talk about the normal, outward normal, this just means perpendicular. So if you hear me say normal direction, that's the direction that's perpendicular to the boundary. The other point that I want to drive home here is that even though this problem talks about boundaries, this actually holds everywhere inside the rod. So we're talking about a rod of some description, some length. We're talking about the heat equation. So we've got our rod here. And the idea is we want to specify kind of what's going on at the boundaries. So let's say that this is a rod of just arbitrary length L. And we want to specify flow rates at the boundaries. Well, I can just think of sort of an inner segment here as being a boundary as well. And so I can think of the flow in and out of this inner segment. So those create boundaries within the rod itself. So everywhere inside the rod, this physical law holds true. And the law basically says that the flux at x equal to 0, so the flux at x, so it's 0t, so the flux at the left endpoint, is equal to or is proportional to the gradient, which is directly proportional to the derivative, u of xt of 0t, and the flux at the right endpoint, u of lt, is directly proportional to minus k u of x of 0t. And this is the point where, and sorry, that should be L of t. This is the point where students sort of shake their heads and they say, I don't get that. Why does it change signs? Well, the easiest way that I can explain this is in a couple of different ways. First off, let's draw some arrows here. So the outward normal is this direction on both boundaries. However, by convention, flow is positive to the right. So if things are flowing to the right, that's considered a positive flow. So the question that immediately comes up here is when you look at these two expressions, why does the sign change? And that's a great question. It's a question that students struggle with in this course, and it's the question I want to answer, and I think the easiest way to answer it is with a picture. So here's the picture that we have. Imagine that this is the x-axis. So we've got, let's say, x equal to 0 on this side. We've got x equal to L on this side. And suppose that the initial temperature profile of the rod is something like let's suppose it's doing something like this. I want to make this look a little bit different. So, yeah. So let's say that it's going here and then here and then something like that. So I'd like to smooth that out a little bit. So let's say that this is initially what the temperature of the rod looks like. Okay, so at the points, I need to make this clearly down. At the point x equal to L and x equal to 0, what can we say is going on? Well, there's a couple of things here. The heat is trapped inside here, and the larger the heat, so this is the graph of U, right? So this is the graph of U of xt for a specific time t, right? So we've specified the time, and this is just the temperature profile. So these are the hot areas because they have the higher temperatures, and likewise these are the cold areas because they have the less hot temperatures. So if I'm looking at the derivatives, then let's say the derivative at this point is what? Well, the derivative at U of x 0t, that derivative is greater than 0 because you can see here that the slope is positive moving from left to right. However, over here at the left endpoint, U of x lt is less than 0 because you can see that the derivative is decreasing. So the question is, what are the flows doing at each of those points? Well, if this is your initial temperature profile, remember that heat always flows from areas of hot to cold. So the flow in this direction is going to be going this way. So it's going to flow from hot to cold, and the flow in this direction is also going to be flowing out that way. What I want you to notice here is that the flow, the direction of the flow, is opposite of the derivative. So let me go ahead and write that down. The direction of the flow is opposite of the derivative. And the way that you can imagine this is, imagine if I think of this line as being sort of a curve or a hill or something physically represented. If I was to drop, say, a ball at this point, it would flow down the hill or down the gradient. So even though the gradient's positive and increasing, the flow is negative or decreasing. So the flow is flowing down the gradient. This is what we mean when we say that it flows down the gradient. And it's the same thing over here. If I was to place an object over here, it would flow down the gradient, but that's opposite of the direction of the derivative. The derivative is negative, which might make you think the flow is negative, but that's not in fact the case. The derivative being negative means the flow is positive, because positive flow is flow to the right. And so I want you to remember that flow is opposite of the derivative. In this case, the derivative is a gradient, because we have a function of two variables, even though it's a one-dimensional problem, meaning only the x direction is the derivative we'd take. Flowing down the gradient is the basic idea. When we get to multi-dimensional problems, it'll be an honest-to-goodness gradient that we'll be looking at. So the flow is down the gradient. Now, the reason this is important is if we want to define, going back to the rod, if we want to define sort of a Neumann boundary condition correctly. So a Neumann boundary condition is a boundary condition that specifies the flux at the boundary. And if we wanted to specify that, then if we just sort of look here at our boundary, then at the left endpoint, if I say u of x of 0t equals r, and r is greater than 0, and over here if I say u of x of lt is equal to r for some r, and that r is greater than 0, then what direction are things flowing? See, this is where you've got to be careful. So the flow here is opposite of the derivative. So the derivative is positive, so the flow is negative. Here, the derivative is positive, so the flow is negative. So this is how you would define negative flow. And that makes sense, right? Over here, it's increasing, right? So your heat is increasing, which means that it's hotter in here than it is out here, so it flows out. And that's exactly what the picture's saying over here. So this basic idea is you've got increasing, increasing, increasing. So it's basically sort of the inverse of this picture. If I wanted to specify flow in the opposite direction, then what I might say is u of x of 0t is equal to, let's say, negative r. And so if that's less than 0, so if we have a negative derivative, so if our derivative is negative here, then the flow is opposite of that direction. So this would be inward flow on the left side, and it would be outward flow on the right side. Once again, if I did u of x Lt equals negative r, which is less than 0. And in particular, one thing I want you to note is a lot of texts will use what's called a physical form. So if you talk about the physical form of the Neumann boundary condition, then over here at the right endpoint, it would be minus u of x of Lt equals minus r, where this side is less than 0. But the idea here is it's negative on both sides, so this boundary condition, writing it this way, is the exact same as writing it this way, mathematically, because you just multiply both sides by a negative. So if you ever see minus u of x equals a negative value, then understand that all people are trying to do there is with the negative value on both sides indicate that the flow is to the left. That's all that's really there for, and that's to sort of mimic this over here, which has a negative for this value. And the reason you can see that is if we want the flux to be positive, then it needs to flow outward, right? A positive flux is outward, right? So outward at the right endpoint means to the right. So positive flux is outward, which at the right endpoint means to the right. So if I want this thing to flow to the right, then I need the gradient to flow to the left. So in order to get phi to be positive, so phi is greater than 0 means that u of x here, since k is assumed to be greater than 0, means u of x has to be less than 0. And this is because k is greater than 0. So you can see here that the flux, which is the flow, and the derivative are going to be at odds with one another because of the differences in directions. Outward flow on the left end is to the left, outward flow on the right end is to the right. And so we have a change in sign that occurs there. So I just wanted to make sure that we go over all the little ins and outs of gradient flow and making sure that we get our directions correct, because it's going to be vitally important for the rest of the semester. All right, thank you for watching.